speaker of the morning is Fabrizio Caselli, who will be speaking on peak algebras, paths in the Bruhat graph, and Kazhdan-Lusztig polynomials.
Thank you very much. Thank you all of you for coming to this talk. Especially I would like to thank all the French guys for not going to see the football match. So let's start with some notation. I will draw with this fancy tool the set 0, 1, and 2 to the end, the set of binary sequences of n, and 2 star, the set of all binary sequences including the empty sequence. And we will always consider the monoid structure of the 2 star given by convolution. And also we will sometimes use this identification between binary sequences and subsets of the integers from 1 to n, just by considering the positions of the ones in the sequence. So for example, if E is 0, 0, 1, 0, 1, then the corresponding set is 3, 5. Okay, so we consider a function on the binary sequences of length n with alpha, and I usually denote by alpha sub e the values that alpha takes from e for each number. So let me give you this definition. We say that such a function is a BB function if it satisfies the following conditions. So for all binary sequence E of length n and all maximal subword of E of consecutive zeros, say E is equal to f times 0 to the j times g, where this 0 to the j is maximal, then I want this condition to be satisfied. So here you see on the left, you have an alternating sum, where these indices are made in the following way. The suffix is always f, as in E, the prefix, the suffix is always g, and then instead of the j zeros, we insert 1 in all possible positions. So here 1, which is in red, as you can clearly see, is in the first position, here is in the second position, here is in the last position. And this should be equal to either 0 or 2 times alpha e, depending on the parity of j. So these are called, sometimes called the Bayer-Diller relations, although they call this generalized Demsov-Bayer relations. And it's an easy exercise to show that the space of BB functions has dimension Fibonacci number f. Okay, so these BB functions appears in several contexts, and I will show you 3 instances of combinatorial structures where these functions appear. The first one is convex polytopes. So if you take a convex polytope P of dimension n plus 1, we can define the flag f vector, and we can see there's a function on the sequences of length n, just by defining f p of e sub e as the number of chains of faces whose dimensions are described by the set SE in the following way. So the dimension of PI should be SI also. And so the theorem of Bayer-Diller, going back to 85, is that if P is a polytope, then the flag f vector for P is always a BB function in our terminology. And moreover, the space of all BB functions of order n is spanned by the flag f vectors of convex polytopes of dimension n plus 1. And the similar result holds for Eulerian posets instead of polytopes. So the second instance is in the theory of P quasi-symmetric functions. So we always have this identification. And I define the monomial quasi-symmetric function in this way. I will index these functions by binary sequences. But as you can see, it's just another way of indexing these functions instead with composition. I parameterize them with binary sequences. So you can see here the exponents are all fixed and determined by the sequence, and the index I1, I2, IT may be any increasing sequence of positive numbers. So here is an example. If you take the binary sequence 0, 1, 0, 0, 1, then SOV is 2, 5, and then the monomial quasi-symmetric function is xi to the 1, as this exponent is 5 plus 1 minus 5. And here we have 3, this is 5 minus 2 is 3, and then 2, which is this S1. Good. There's this theorem of by Bilera, Xiao, and Wilgenberg. So they show in this paper, among many other things, that if you take a quasi-symmetric function like this, so you consider the coefficients as the values of a function alpha, then we have that this is a big function if and only if this coefficient function is a big function. Okay? If you don't know the definition of big function, it doesn't matter. You may take this as a definition since it is a characterization. And let me just note that the space of big functions actually is a subalgebra of QC. So the third instance is in the theory of Coxeter groups. So we consider the Coxeter group WS, Coxeter system. I denote by T the set of reflections. And I define the Bruhat graph as a direct graph with W as vertex set. And then we put a directed edge from X to XT, where T is a reflection if the length increases from X to XT. So, and let me just remark that the Bruhat order is given by the transitive closure of this directed graph. So if you've never seen this before, maybe you have seen the structure of the Hasse diagrams of Bruhat intervals. These are always graded posets. Actually, they are Eulerian posets. So they look like this. And the corresponding Bruhat graph is obtained from this by adding some new longer edges. They always have odd length, but this may be any odd number. Okay. Of course, you have to consider all the edges directed from bottom to top. And here, so when we consider a path from U to V, this may have different lengths. Okay. So we may take these longer steps. So if we consider what is called a convex ordering on the reflection, or sometimes called a reflection ordering. So this is a total ordering satisfying some additional conditions. We can make this definition. If you take a path delta in the Bruhat graph, so where the labels are T1, T2, Tr plus 1, then we define the corresponding descent string in the following way. We just record the position where the labels go down in this order. So we put a 1 whenever we have a descent, and we put a 0 whenever we have an ascent. So let's see the variable in this context. We consider two elements U, V, and W, and we denote by B and UV the set of all paths in the Bruhat graph from U to V of length n, and we fix the reflection order. So the function alpha here is defined this way. Alpha U of V is a function from the set of all binary sequences to Q, and it is given by this. This is just the number of paths in the Bruhat graph of length, the length of U plus 1, whose descent string is smaller or equal than E. Where this order is the component twice loss. By this I mean all the entries of T delta must be smaller or equal than those of E. And we have this theorem of Francesco of 98, which says that, first of all, these numbers here do not depend on the choice of the reflection ordering, and the function alpha uv restricted to n is a BB function for all n. So it often happens, and especially in these three instances, that if you have a BB function and you perform inclusion-exclusion to the BB function, you obtain another function that we may call a BB star function. Okay? And it often happens that this is a very interesting function. And so maybe the first thing I want to address is to find the BB star relations explicitly. So which are the relations that are satisfied by such functions? Some of these are already known, and particular, we know that if beta is a BB star function, then beta f is equal to beta f bar, where f bar is the complement string of f. But this is not enough, and the other relations are as follows. One for the notation, we denote by E check the sequence which is obtained from E by changing the last digit of E. And so here is the result. The first result is that if beta is a function of 2n, then this is a BB star function if and only if you satisfy this rather simple relation. So you have beta EF plus beta E check F equal beta EF bar plus beta E check F bar for all EF into n. Okay? E times F. So let's see what happens in our three instances. So in the case of the flag F vector, if you apply inclusion, exclusion, we obtain the flag H vector. And but I don't want to talk about this. So let's see what happens in the peak algebra. So here I will denote by Fe the fundamental Gessel quasi-symmetric functions, which can be defined this way. This is the sum of the monomial symmetric function indexed by sequences which are greater than E. And so if we consider our definitions together, we have that actually a quasi-symmetric function expanded into the fundamental basis is a peak function if and only if the coefficient function is a BB star function. So now I want to exploit these conditions to find a new basis for the algebra of peak functions. So for this I need some technical definitions. So we take a sequence E which is made in this way. We have A1 zeros, then A21, and so on. Or we have A11, then A20, and so on. Okay, where these exponents are all positive. And we say that this sequence is admissible if it's not constant. So we have R is greater or equal than 2. And all the internal exponents are even. And in this case, we record the length of the first sequence by calling it the sine of E. And we also say that E is finally if all but the first exponent are even. Okay? So, let me give you this further definition. If we take a binary sequence H, I denote by GH the set of all binary sequence, or this should be set all binary sequences of length n-1 that can be factorized in the following way: E1 times E2 times Et plus 1, where the length of EI is the Si minus S sub I minus 1, and I want all these sequences to be admissible, and the last one should be final, okay, according to this definition above. So I'll just make a quick example here. If you take H to be 0, 0, 1, 0, 0, then here E must be the product of two sequences, E1, E2, where E1 is an admissible sequence of length 3, and E2 is a final sequence of length 2. And if you look at this definition, you will certainly compute that E1 must be an element of this set, and E2 must be like this. You see here, you cannot have internal exponents of odd length. Actually, here we don't have an internal exponent at all. The definition. So in this case, GH is made by multiplying any element of this set with any element of this set. And so in this case, we have 8 elements in G of H. So if E is in G of H and it has this factorization, we let the sine of E be the sum of the sines of these factors. And we define this quasi-symmetric function D of H as the sum of fundamental quasi-symmetric functions with this sign in front. Okay? So, if we say that a sequence is sparse if it does not start with 1 and does not have 2 consecutive ones, and we denote 2 star sub s the set of sparse binary sequences, we can easily check that the set GH is empty, and so DH is 0 if H is not sparse. And here we have this theorem, namely that these quasi-symmetric functions are actually peak functions, and that yes, this set of DH, say the DH which are not 0, together with 1 is the basis for the peak algebra. And moreover, we have this special property that will be used in the proof of the main theorem, is that if you have a peak function that is expanded in the fundamental basis in this way, then you may obtain the expansion with respect to this new basis just by deleting all terms which are not indexed by non-sparse sequences and substitute the fundamental quasi-symmetric functions with these new peak functions. Okay? So let's see what happens in Coxeter groups. So remember, we have defined this alpha uv sub e in this way, and we knew that this is a baby function. So if we apply inclusion or exclusion in this case, we obtain, okay, this is the definition, but of course it's an easy exercise to show that in this case beta uv is given by the number of paths whose descent string is exactly e. And so we have that this function is a baby star function. Okay? So these are, by and large, all the ingredients that will be needed in the proof of our main result, which is a new combinatorial formula for Kazhdan-Lusztig polynomials. But to express this formula, we need to introduce a new combinatorial concept, the concept of a slalom associated to a sparse sequence. Okay? So here is a picture of a real slalom, where you have to go around these red and blue flags. And you have to do it as fast as you can. But in our case, we are not interested in doing it very fast. We will be interested in how many ways we can do this and in which ways. Okay? So I will give this definition of an H slalom giving an example. I hope the example will be general enough for the general definition. So you take your sparse sequence, such as this one, and you write it just below the x-axis, starting at position 2. Okay? From 2 on, with this sparse sequence. Okay, then we put a star here in position on point 1, 0, and then we add a star above all ones of the sequence. Okay? So note that there cannot be 2 consecutive stars because the sequence is sparse. And then to record the length of the sequence, I put a chessboard flag here and here. Good. So now the sequence is no longer needed, so we can erase it. And we start building our track for the slalom. So this is actually green, you see. This is a green segment starting from the first star and up to 1 unit less the following star. Just below the x-axis, you may think of this as at height minus a half. Okay? And then we do the same for these others. This is green, and here, for the last star, we do the same, but we color this segment in red. Okay? So it's good that the colors are visible. So this is the track of our slalom. So what is a slalom? A slalom is a lattice path that starts from the origin, which is allowed to do steps only 1, 1 and 1 minus 1 with the following further conditions. It cannot pass through the stars, and it has to cross all green segments exactly once, and it must remain above the red segment. So maybe I'll show an example. Aha! The lattice path is not visible. I don't know how much time to prepare this lecture.
No.
It's really not just visible on the screen, but
Which is the color?
chalkboard black. It was just black.
Did you do it on the chalkboard?
Yeah. So let's try to do this. We have this star and the segment, and another star, segment, star, segment, star, red segment, and just one. So let's see. So we don't have to cross the star, and we have to cross the green segments exactly once. So you can probably maybe do something like this. Then we have to cross this segment once. And then we have to cross this once. And then we have to remain above this red segment. So push. So at the end I deleted the red segment, and maybe you can see the red and blue flag, and then so the invisible lattice path go around this flags. Making a slab.
Is you exactly once or at least once?
Pardon?
You cross exactly once or at least once?
Exactly once. Exactly. So this is a formal definition of slab, or maybe we can skip it. And here we have the definition of our main object, which is this polynomial omega h. So it has a sign in front, and then you have the sum about all h slaloms gamma. And for each slalom, you consider the power, the monomial minus q to the number of down steps of gamma. So here I have an example, but I think. Oh yes, the parts are this. So if you consider this sparse sequence, H, then there are exactly these H slaloms in this case. And so if you look at the 4 paths in the first row, all have exactly 5 down steps. So they contribute this minus 4q to the 5. And then there are 5 paths making 4 down steps, and they contribute this 5 q to the 4, and finally there is only one step, one path, this one with making exactly 3 down steps. So the main result is the following. Given a Coxeter system WS, take 2 elements U shorter than V in Bruhat order, and we consider we let P, U, V, Q be the Kazhdan-Lusztig polynomial of UV. The theorem is the following. And in particular, that this Kazhdan-Lusztig polynomial P, U, V of Q is the sum of all sparse sequences of H. Here you have the power of Q, here you have the rank of the interval UV minus 1 minus the length of the sparse sequence divided by 2. Here we have the number of paths in the Bruhat graph from U to V having descent string exactly H. And finally we have this omega polynomial which we are defined in terms of constants. I think I stop here because thanks.